Okay, thank you very much for organizing this conference. It's exciting to still have these conferences in our local communities between, our local universities. So I'm excited to present today some work that we've done, submitted recently on thinking about the transition path ensemble in a thermodynamic way. So what we're really thinking about is reaction theories. So you have some system that you're interested in, and we're going to assume throughout the talk that it's at equilibrium. So if you have a really long ergodic trajectory and you have two subsets A and B of your state space that you're interested in understanding something about the reaction between, a really long ergodic trajectory is basically going to fluctuate between these states A and B many, many times if you watch it long enough. And one of the kind of fundamental problems in chemistry or in many, many fields is to take this microscopic picture of your system and extract something about the overall reaction, which is what I'm showing on the left here. Is just you have A and B and some rate constant for the transition between them. So reaction theories are generally trying to relate these two pictures. What's the relationship between the microscopic system dynamics and this sort of mesoscopic picture of an overall chemical reaction? So one example of a reaction theory, which most of us are probably familiar with, is transition state theory. So transition state theory basically conceptualizes this activated complex in between A and B. This activated complex is basically the gatekeeper species between A and B that the system has to pass through as it does this reaction. And transition state theory then derives from this idea of the transition state a rate constant for the reaction, and it works well for a large class of reactions. But as we start to think more about biophysical contexts, where often our molecules are larger and floppier, this idea of a transition state isn't necessarily applicable. There could be multiple metastable states throughout a reaction. There could be multiple pathways that the system takes between A and B. So we kind of need a more quantitative theory of the entire reaction. So this was developed already as the field or the theory of transition paths. So the basic idea is that we think about the transition path ensemble. So this is the set of all of the trajectories that go between A and B. So most of the time, your system's just bouncing around in one of these two stable states, but it occasionally makes these excursions between A and B. And there's many, many different ways that the system can do that. So if you take the ensemble of all of those trajectories, this forms the transition path ensemble. And then we can statistically analyze this transition path ensemble. So the key mathematical construct to think about the statistics of this is something called the committer. So the committer is a function of the state space of the system, and it gives you the probability that if you initiate a trajectory from a given state, the probability that that system will go to B rather than to A next. So the committer has some really nice properties. First of all, it takes the entire state space of the system, and it maps it to an interval between 0 and 1. Where it's 0 in A and 1 in B. You can also identify the transition state ensemble as this Q equals 0.5 surface. So these are all the configurations of the system that have equal probability of going to A or to B next. And it's been discussed in the literature recently that this committer is kind of a very good quantitative definition of the reaction coordinate. So when we draw this one-dimensional picture of a reaction with some energy landscape, you can really think of the x-axis of this picture as the coordinate. So it's kind of the true reaction coordinate. So what we did with this is we looked at the committer and thought, well, the committer is giving you the probability of an event occurring in your system. So let's explicitly model what those events are. So when selecting these trajectories that are part of the transition path ensemble, you're selecting trajectory segments based on two criterion: when they leave A and when they reach B. So we define these two random variables as the trajectory outcome S plus and the trajectory origin S minus. So these variables have values of either A or B, and they tell you where the system's going next and where the system just came from. And both of them can be related to this committer function. So when we have these two random variables, this allows us to take the entire equilibrium ensemble and split it into 4 sub-ensembles based on where these trajectories are starting and ending. So starting in the top left of this figure, this is when your system is in your state A, which you define however you want. And it's just bouncing around. So it can leave A, it can come back to A many times. It's just kind of sitting in that stable state. So this is the A to A trajectory subensemble. And then occasionally your system will make these excursions over to B. So that's when the system moves into the second subensemble on the top right. This is our transition path ensemble. So all the trajectories that go from A to B will be part of that subensemble. And then continuing around the circle, you have the B to B trajectories, and then the reverse transition path ensemble that goes from B back to A. So if we look at this four subensemble, if you think of a really long equilibrium trajectory, it's continuously transitioning between these four subensembles, and the flux of the subensemble transitions from transition path theory, you can derive the rate constants for the reaction from the statistics of this switching between subensembles. But then thinking back to this idea about reaction theories and trying to relate microscopic system dynamics to this mesoscopic picture of just an A to B reaction, what we're really looking at here in this picture is a relationship between the system state and these trajectory subensembles. So we can statistically quantify the total relationship between these two random variables, which we do with the mutual information between the subensemble, which we give the name S, and the system state phi. What we can get from this immediately is that the mutual information between the subensemble and the system state, you don't actually need to know the whole state of the system. All you need to know is this one coordinate, which is given by the committer. So the committer is a sufficient statistic for describing the relationship between the system state and this trajectory subensemble picture of the overall reaction, which is kind of why it's the ideal or true reaction coordinate. Okay, second thing we notice about this picture is that even though our equilibrium trajectory was time reversible, now we have the irreversible transitions between four subensembles. So in particular, we notice that the two subensembles where the trajectories are actually transitioning between the stable states have a net flux, and then A to A and B to B subensembles don't have any net flux. But when we consider now the joint dynamics of the system and these four subensembles together, there's now entry production that we can calculate, irreversible entry production for the transition path ensemble. So this measures the time irreversibility of these transition paths. How many more steps does it take towards B as opposed to towards A in the four transition path ensemble? And we find that this entry production rate is equal to the mutual information that's generated by the system about the trajectory outcome. So kind of giving you an idea of which dynamics of your system are actually relevant for getting the system between A and B. So what we can do now with this entry production is learn a little bit more about the reaction mechanism, and in particular, which system coordinates are important to describing the reaction mechanism. So often your system is very high dimensional and you don't want to keep track of all of the degree of freedom in your system. So ideally you want some sort of reduced representation to describe the reaction, but choosing those coordinates isn't so straightforward. So here we can actually use this entropy production in the transition path ensemble to identify relevant coordinates. So as a sort of example here, we consider a bistable energy landscape, which is shown in the bottom left here. So the purple contours are showing the energy landscape. The gray lines are showing the committer for the landscape. And I've also shown here in the black dashed line sort of the true reaction coordinate passing through both of these energy minima. But if you didn't know beforehand that was the reaction coordinate, you would choose coordinates x, y, x and y for the system to describe the reaction, and they might not perfectly align with what this reaction coordinate is. But what we can do is actually take this entry production of the transition path ensemble, and under certain assumptions of the dynamics, we can split it up into a component from the x dynamics and a component from the y dynamics. And the entry production of this, the entry production from the x dynamics is going to tell you about how informative those dynamics are about the reactivity of the trajectory. So this really gives you a quantitative measure of how important x is to describing the reaction. And in particular, we can find that if x is this committer coordinate, the true ideal reaction coordinate, then that's, again, the only coordinate you need to keep track of, and it will account for all the entry production of the system in the transition path ensemble, which means that it's kind of a perfect grain representation of the transition path ensemble. So for these general coordinates x and y, we can consider how does the entropy production of the two coordinates change as we rotate this underlying energy landscape. And we see basically exactly what we expect. So when this angle theta is 0, x is the reaction coordinate and y is completely irrelevant. And we see that reflected in the entropy production in this plot B, where x has all entropy production and y has none. And then as we rotate this energy landscape relative to these xy coordinates, we see that there's a trade-off in dependency of x and y, and they cross over. Yeah, so that kind of gives us a quantitative measure then of how important that coordinate is to the reaction. So to summarize, we're thinking about reactive trajectories and trying to relate a microscopic picture of an equilibrium trajectory to overall reaction properties. So by taking a thermodynamic perspective on transition paths and looking at some information theory aspects, we find that we can completely quantify statistically what the relationship is between underlying system dynamics and overall reaction properties. And further, we find that there's entropy production in these dynamics that tells us something about which parts of our system are actually relevant to describing the reaction. So the main takeaway that I want to highlight here is that all of the tools and theory that have been developed in recent years to study non-equilibrium systems, we can apply to studying reactions that are occurring at equilibrium. So we could find coordinates that have a lot of dissipation in these ensembles. We could estimate the entropy production for different coordinates in the ensembles to get a better idea of what the reaction, or what's happening during the reaction. And I've also just put our archive link for our paper there on the summary slide as well. So thank you very much for your attention, and I'm happy to take your questions.